In the episode today, we will dive in much more deeply into the big topic of batteries. In particular, we will have a look into batteries in the power range of 1 to 20 megawatt, and we try to understand better where it is feasible to request a certain battery size and what is not really recommended because it's just wasting time and resources. And from the grid perspective, it is very unlikely to be connected. So I've chosen here as example an area north of Bochum. It's around Hörstel. And first of all, we go again from macro to micro. We want to understand a little bit what's going on in this area. So what we do is we select storage and we select whole of Germany above 1 megawatt. We select in operation and what is connected to the extra high voltage network and medium voltage network, and we load plants. So what we see, we do not see much here. Here is a battery actually that is already in operation, a smaller one. And we have here one battery, okay, which is 3 megawatt. We have here some small batteries. Oh, okay, that's the big one. And here we also have a decent one. Okay, but we are operating here and we see there is no battery installed yet. So let's have the next step. What is planned actually? Are there batteries already planned? Oh yeah, okay. We see there are batteries planned. Here is a battery plant, like 6.7 megawatt. Here is a battery plant, 3.5 megawatt. Here's a battery plant, 2.5, and here's a battery plant, 5.5. So we get an idea of what kind of batteries are there already planned. It's not those huge utility scale batteries, rather like also not small ones, but I would say like decent ones for the grid. So, but we are focusing now on this area. We want to connect to this substation here, Station ECI. We check what's happening here. We see there is like around 60 megawatt connected. Solar power is connected, wind power is connected, and we have a bunch of transformers because that's also a load center here. We see what kind of transformers. It's a radial feeder. What this means we will see soon, or we already see. And here we have Station Hörstel, which has around 68 megawatt. So in total, they get together to 128 megawatt. So what's important here? When we go a little bit deeper, we see that there seems to be a lot of transformers. This is also because it's a load center and we have to fulfill the N-1 criteria. And we also see these are two radial feeders, which means there is only one line leaving this kind of area here, which means that it's not meshed. Yeah, a meshed area is something like this substation here, for example, and the line goes here and the line goes here and it splits up again. So we are a little bit limited, but this also helps to understand limitations, because if we click on this line, we see we have two circuits, 6 cables, and roughly 246 MVA. So that's our maximum capacity that can be transmitted through, or this, which can be conducted through this power line. But as a rule of thumb, I said it in the video before, we can only assume that we are capable of using half of it, because then always needs to be like a safety margin in case one circuit, for example, is destroyed. We still have another circuit. So we can compute here, we can have around 120, 130 MVA. So this gives us on the first view like a problem, because we get here around 70 megawatt and here it's like 60 megawatt, which gives us around 130 megawatt already. So there's not much capability for this line to have even more power on it. So, but thankfully we have the substation analysis report, and we do it first for this substation, which will result in this report here. I can show it. It shows, okay, it's a generation alone substation, so we have to fully account all the connected power to the substation, which is around, like 68 megawatt. So we can have a look again here how much it was. Okay, 68. And we also do the substation analysis on this substation. We click here. I will explain this later. We do apply. And we get also for Station ECI a substation. It's also a load substation, which we can see here. In total, we have a surplus anyway, surplus generation at this substation, but we have a maximum net load, so load minus generation, of 32 megawatt. So it can be a sink, a load sink, but we can also have excess generation, which is up to 35.5 megawatt. So we have to like include here an export of energy of roughly 35 megawatt. This is 68, 35, so we get up to 105, 110 megawatt, which means we can assume a battery storage not more than like 20 megawatt that we are building here, and this is already optimistic. If we make a grid connection request, because the system operator, he will look, okay, how much generation is affecting this kind of network area, what is the load, and does it exceed, if also the battery is injecting energy, this kind of power line here? And if yes, then it's rejected. So it's not a good area to request, for example, 40, 50, 60 megawatt or more of battery size. But what's a good size now to request? So we understand now the constraints, which are mainly coming through this line here. And they are also not like going away in the near future. If we have a look at the grid development plan, there is a like line planned from here, 60 MVA are planned, but it doesn't really affect here this area. So what we can do is we have a look into our loads that are planned maybe here in the near future, but we also see nothing new is planned here, so the load won't change much. So what we do now is doing a substation analysis based on our grid neutral compliance, which means we try to find a battery that perfectly fits into the generation envelope at this substation, which means we design a battery size and energy that is not increasing the load sink, and it is also not exceeding the exported energy, which is important because otherwise we might risk to exceed the power on the line, and then it's very unlikely to get a grid connection allowance from the system operator. So how can we do it? We can choose certain scenario. If we are conservative, we take conservative. If we want a more balanced approach, we take balance. If we're optimistic, we take this. If we take balance, we see that we consider the 18th percentile of the generation of the last 12 months that we compute in 15-minute steps. And we like consider it for like weekends, for weekdays, but also for different seasons. So it's like dynamic. What we also do is we can define a certain safety margin below this, which is now here 10%. And we can also make a tick for enable load import. But if we do that, it's from the definition not a grid neutral storage anymore, because now we start to also draw energy from the grid when there is not a surplus generation. So we can like increase even the load in this area. So let's keep it for this reason at 0. We can define a certain C rate range, and we can define our charge and discharge availability at full power. So if we get out a recommended battery size of 10 megawatt, it means we have 30% of the last 12 months of the whole time the capability of charging at full power and 60% of discharging at full power. We click apply and the substation report is made for us. The finished substation analysis can be seen here for this substation, and we also get like a good overview about important metrics here. One important metric is how long we have a surplus of generation, which is 11 hours per day, roughly. We see, as said before, the load and also the minimum net load. But what is very important is the recommended best power here. So it gives us a recommendation for a battery that would fit into this network area and also an energy. With respect to the different seasons and the different hours and the headroom, so the safety margin and the export limit that we have defined here. So this helps us a lot to understand how the generation was, but also like what kind of battery would fit into this kind of area very well. And it helps us to get, of course, into a discussion with the system operator, but also to make a practical approach and not to overestimate the capacity that the grid has at this kind of location here. Another example I wanted to show is this kind of substation. So we can also do the analysis here. It's like UV Körbelitz. If we click on it, we see what is already connected. We see it's a good mix, also solar and wind power, which is good because if it's more mixed and if there is like a high surplus generation, then like a grid neutral battery would fit in much better into a certain network region. So we can also start the substation report here. Let's say we are conservative and we click apply. And as a result, we get also here an analysis for UV Körbelitz. And I think what's very interesting is that it's like smaller. Like here, the recommended best power is 2.5 megawatt and the recommended best energy is 4 megawatt hours. This becomes also clearer if we have a look at the metrics overview, because here we can see, okay, the surplus duration is only 4.8 hours per day. And there is quite some load in this area. So the possibility of the grid neutral battery to like interact only within the generation envelope in this area is much smaller than in the station before. This is why the recommended power is also smaller. Okay, and this is everything about small batteries.